Sorry about that. I had it stop right in the middle on accident. When we get here, as long as we know these are equivalent, we can say this is 4L plus 4L equals 28. So equal L when a lilikoi is 7½ cups. And therefore, 3 units of water equal 4. And we can solve for W. And 14³ cups of water for 7½ cups of lilikoi, which should give us 28 cups of punch. Alright, but let's prove that. So if we have, again, 3W plus 4L, we want equal 28. That means 3 14³ plus 4 7/2 should equal, cancel, 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 14 plus 4, which equals 28. Check and check. Sorry, it got really dark there. Alright, that is, oh, but that's just for my own benefit of solving for it. Let's take a look at their work again. It looks like there's one arithmetic mistake, but he used ratios to solve and is correct, so that's fine. Eileen, though, is a little different. She listed what we would call separate ratios all the way through. So ratio, 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 not ever having moved to the rate. So there's an underlying sort of message here that there's a constant rate that she sort of missed. And so she listed ratios but didn't use rate. That would be my take on her. Okay, I'm going to turn on my light. Okay, moving on to problem number 4. This is a cute one. Toddler and his mother walk on a sidewalk from the car to the playground entrance in the same amount of time. Who walks faster, the toddler or the mother? Explain. Again, good for discussion, but my guess is most people will know that the toddler and the mom, even though the toddler might look like he's having to put a lot more effort in it, he is going the same rate. But consider that many students believe that the toddler does walk faster. Why do you think they think that? I think it comes back to the idea of seeing rate as effort or how hard. But my guess is that it's a little bit easier maybe to think about in terms of distance equals rate times time. And in this case, I feel like we would just know that the distance, the travel they traveled together is the exact same and the time is exactly the same. And if we looked at the rate that they traveled as distance over time, knowing these two numbers are the same for both, that means it must be at a constant rate. All right, let's take a look at number 5. Cassandra perceived how fast her bathtub was leaking. She got a large container and put it under the faucet until morning. She checked it periodically during the day to see how much water was in the container. Now, she did something I think that is unique, or I like her thinking. She, and it's real world, I like that too. But you'll see right away that she measures at 7 a.m. 7 a.m., 8:15, so okay, that's an hour and 15. And then 9:45, and then 2:30, which is reasonable for a person, but it's not helping us as a math problem, which so often are a little bit too easy to solve because we give constants. So let's take a look. Does the table indicate the water drips steadily or did it drip faster or slower during parts of the day, and explain. All right, that's probably the first question. So this is question number 5. My take on this would be to create a table. We'll have time, we'll have elapsed time, and how much water was added. So at 7 a.m., we're going to say elapsed time is 0, but there's 2 ounces. This was a.m. And then the 8:15. And if you haven't already, you can go ahead and pause the video and do it yourself and then fast forward. You don't have to watch me do all of this, but that's fine. This amount of time that passed through is 1 hour and 15 minutes. Yeah, and so that's 75 minutes of elapsed time. The amount added was, it went to 12 ounces, but I'm just going to say 10 ounces were added. And then our next time was 9:45. The elapsed time was 90 minutes now. And how much was added? We went from 12 ounces to 24, so that's 12 ounces. And then finally 2:30 p.m. That's actually 285 minutes and 38 ounces of new water was added. In the final 5:15, 165 minutes from the last interval check, and then 22 ounces gone. Now, I think you guys know where I would go with this, but I'm going to create a third column and analyze what we're getting for ounces added for the amount of time passing, and that's around 2/15. So our ounces per minute is that, and for the next one we have 12/90, which also simplifies to 2/15, and then we have 38/285, which also simplifies, and I think you got the idea. This is 22/165, which simplifies, surprisingly enough, to the same rate. That's our conclusion, that the drip is a steady rate. And let's check out the question, see if we answered everything. If you include any decimals in your calculation, explain exactly what they mean in the situation. I don't think I did. Why do many students think that the water didn't drip at a constant rate? I think that's a good question. Because the time periods are so different, I think that sort of leads people to think that there's just different amounts of water, and the assumption is the time segments would be the same, so you'd expect the rate to be different. I think it's just a nice question because it's real world, but it's also a analysis of the rate underlining all these different ratios are the same. What else could we say? You'd have to really extrapolate to another level of difficulty to see the actual rate. I think that's a little tricky to see as well. And the numbers don't look at all similar at first. So there's that. Even these fractions don't look very similar. That's my take on that one. Number 6. I should use a darker pen probably. I don't have one right now. I won't get to it yet. So number 6 is Ariana is driving at a rate of a half mile. Whoops. Is driving at a rate of a half mile per minute. Oh yeah, and she started at home and has driven a while now. How far does she travel in a little smidge of time, such as a half a minute. Alright, so this question is just saying, sort of working backwards, like we're not using classic units or anything really more difficult than that. So I would say, oh, I like my way of handling it. So in 1/2 mile, we traveled in 1 minute. And you might guess in 1/4 mile, so we traveled in a half a minute. I think that's one easy way to look at it, without using decimals or anything. Now the next one is looking at it as if we went to units. So if we started with a 1/2 mile in 1 minute, but then we look at 1/10 of that period of time, I would multiply 1/10 by both of those. So 1/10 of 1/2 is 1/20. So we would travel 1/20 of a mile in 1/10 of a minute. So check. 7 minutes later, she checks her watch. She was 3.8 miles from home, and we want to know how far from home she was when she checked her watch. And I would think about, like, as far as the time I think she's looking at. So how long has it been since she was home? So let's take a look. If she's traveled 3.8 miles, I would look at it like this. We travel 1 minute per half mile, and then we've traveled through 3.8 miles. Can you still see it? Yikes, sorry about that. Sorry, so I'm right here. Boy, I have to take my time. And so all that is 3.8, 1/2. So doubling both of those gives us 7.6 minutes is how long it has been since she was home. That's all for that one. Alright, number 7. Or did I finish that one? Why do you think students think that, oh, no, sorry. 7 minutes effort, do not use any form, we didn't use any form algebra. We explained our solution, I think, fair enough. Let's go on to Heidi. And Heidi's question is, sorry. The length of 5 of Heidi's steps is equal to 3 of her mother's steps. If Heidi walks 24 meters, how far would her mom go in the same number of steps? Draw a picture and explain your solution. Can you solve it without giving a specific distance to Heidi's steps? All right, all reasonable questions, which I think sort of cry out for a double number line, and so that's what I'm going to use. For steps, we have 5 steps for mom, no, 5 steps for Heidi, and 3 steps for mom. That would be 10 steps for Heidi, 6 steps for mom, and what we're looking for, we want a distance, but I haven't got there yet. I'm just trying to come up with some ratio, so we would end up at 25 steps for Heidi for 15 steps for mom. That's one way to look at this one. And I would try to understand, oh, I should get a new piece of paper out. So taking this ratio, we know that it's 5 Heidi steps for 3 mom steps. If H is the length of Heidi's steps, So 3/5 H is a single mom step. I think that makes sense, right? So let's take a look at the lengths. Is a double ratio as well, or a double number line? If we take 5 Heidi steps is 3 mom steps, but think about those mom steps is 3/5 H. Does that make sense? And then 10 Heidi steps is equivalent to the mom, which would be 6, which would be 3/5 Heidi steps. All right, so with that, what I want to come up with is a ratio. A ratio that compares 24 meters, or a distance of 24 units. And then within that will be, I want to know how many 3/5 units will go into that. Now, looking at this problem, I don't know if it's clear, but what I'm asking is, just like if I asked how many units of 3 would go into 24, I would represent it that way. This is how many 3/5 units are in 24. So this is Heidi traveling 24 meters. We know the mom travels farther, but the idea is that this represents 3/5 of the total distance mom traveled. This is why I'm trying to figure out how many 3/5 will go into 24. And then I'll multiply both sides by 5, get 120. And that gives me 40 meters of distance for Heidi's mom. Okay, so then the second part of the question is, why do so many students find it challenging? I think this one is basically because the steps aren't even. There's not a simple ratio, I don't think, to solving it. I think we must use the number line or algebra, and without algebra, we have to think in terms of ratios like we talked about. And I'm not even sure we need a unit rate for this one, and that's one reason I like it, because it's sort of unique. All right, let me move on. Talk about problems, why I like them and everything. The number 8. Consider this scenario. You've paid $22 for an 8-gallon. I'm going to switch to a darker ink. But anyway, I paid $22 for 8 gallons of gasoline. And write an equation that allows you to determine how much money you'll pay, P, for G gallons of gasoline, and then read the rest of the part below. All right, so let me pause. Okay, let's take a look at the gasoline problem. Let's say you've paid 22 gallons, you paid $22 for 8 gallons of gas. Write an equation that allows you to determine how much money you'll pay, P, for G gallons of gas, then read the rest of the part below. All right, so just an overview. We're moving pretty quickly here across math models. So just to step back a little, problem number 8 is taking us from, we set up tables. I think we did a little bit of graphing. And then we are moving on to algebra. And the trick is, I think, one of the tricks is we see weaknesses in our kids' algebra skills, is to look back at a graph that represents the algebra, and if the graphing skills are not are clicking for the kids, to look back at the tables, and then move backward and forward between these three things to help our kids. So again, to explain the relationship between, I think, a pretty simple ratio of what this, by the way, is a ratio, but we will get to the gas part. And I think the easiest way, again, is to, let's go ahead and jump to the graph. And I would basically put some benchmark numbers up there. This is the dollars. Sorry, that would help. This is the number of gallons. And our benchmark numbers are here. We have $22, and that bought us, sorry, I have to look back at the problem, 8 gallons of gas. And that's a nice benchmark, but then let's simplify it a little. Let's cut this in half to 11 gallons, excuse me, $11 would buy us 4 gallons of gas. All right, now I would want to know dollars per gallon is the unit rate, and knowing this is a graph, and $0 by 0 gallons of gas, I can know my starting point. So I have this graph here that will help me find an algebraic expression. And one way to look at it, and I just thought of this and I don't know if it's good or bad, but I'll share it with you, is that I want this unit to be per 1 gallon, let's say, is my goal, to make it a unit rate. Sorry, that's supposed to be a 1. So do you agree that's exactly cutting this by fourths? So I'd have to divide this by 4 and come up with a unit of 1. And if I did that, do you agree I'd have to divide 11 divided by 4 as well to get my unit rate? And 11 divided by 4, of course, indicates that we have 11 gallons, or excuse me, 11/4 dollars per gallon. And so the price equals 11/4 of a gallon would get us $1 of gasoline. Does that make sense? And so so again, the price you pay for 1 gallon of gas is 11/4, if that makes sense. All right, let's take a look at the next one. Oh, we're wrapping up. Oh, did I miss any parts too? No, that's good. Oh, I'm sorry, there's still a lot more thinking. Boy, we're almost done here. Do we have another page? We do not. So I probably went too far. Why don't you take number 9 as your homework problem to work on your own? I think it looks suspiciously like the one we just worked on. Feel free to use a graph. I'll walk through it. Water's running the holding tank at 2 gallons per minute. Someone from the water company arrived at noon to monitor the situation. Let noon be the reference time. Write an equation for the situation. Be sure to tell what your letters represent. Use your equation B to explain the negative values in the representation mean, and a quantitative solution, e.g. +2 times -3. All right. Well, just, I know it's confusing, so this would represent, would be the water leaving the holding tank. That's why it would be a -3, because it's leaving. I think that should be it. Thank you for watching. Sorry it goes long, but you know how it is. I guess our class is pretty long. There are some notes here that I'll leave that be. Okay. Have a good day, guys. If there's anything else, I'll write it in the notes attachment for the assignment. Thanks for watching.